Okay, welcome back everyone. Thank you for coming to the last of these 4 lectures. So in the previous lecture we started talking about the Erdös-Ginzburg-Ziv problem, and so I wrote the problem again here. So in this problem you're given 2 positive integers m and n, and you're asking about what is the minimum integer s, so that among any s points in the n-dimensional integer lattice z to the n, you will always be able to find m points among those s points, so that the centroid of those m points is also a lattice point in z to the n. And we drew some pictures last time to sort of, for n equals 2 and m equals 3, to sort of make the problem more clear. And so since we'll be talking for this problem, well, we were talking for this problem already for a while last week, and we'll be talking about it for a while more this week, we need a notation for the answer. And so we denote the answer to this problem by s of z m to the n. So that's called the Erdös-Ginzburg-Ziv constant. And this notation z modulo m to the n suggests that this problem can be translated in a problem in z mod m to the n. So then it's a problem about sequences or multisets in z mod m to the n. And so that's why the notation is chosen that way. Okay, so we also already talked about last week about the fact that sort of there's only few known exact values for this. And so the main goal is maybe to understand the growth behavior of this function, to estimate the growth behavior. We also talked about the fact that if you fix the dimension n and let m be large, then this is reasonably well understood. So for fixed dimension n and large m, we have that this s of z m to the n grows linearly with m. So it's easy to see it's certainly at least m, and it's at most a constant depending on n times m. So that means it's upper and lower bounded by a linear function of m, so it grows linearly with m. And so also, as we discussed last time, so Alon and Dubiner proved this result about the linearity in m for fixed dimension n already 30 years ago. And so then this value for this constant Cn was improved recently by Zakharov to something just exponential n, but under the assumption that m has only prime factors which are large with respect to n. So we discussed this last time. Okay, but what we also said last time is that much less is understood in the opposite parameter regime. If you fix m and let n be large, how big is this then? And that's sort of our main focus today, this question. And then, so then last time we talked about that we can reduce this question to the case where this fixed m is a prime. And this reduction is via this lemma, which we started proving last time, but then unfortunately there was this alarm, and so we had to interrupt. And then I finished the proof in the second part of the lecture, but the video was only uploaded on Friday, so I'm not sure how many of you have had the chance to see the video in the meantime. But in any case, so I think last time we sort of saw the gist of the proof, and then sort of if you want to see how the rest of the proof goes and you haven't watched the video yet, you can see it on the video. So for now, let's just believe this lemma. So so this lemma says that if m is a product of 2 numbers k and l, then s of kl to the n can be upper bounded in terms of this Erdös-Ginzburg-Ziv constant for k and l. So that means if m is a product of 2 numbers, we can bound this in terms of the sort of analogous Erdös-Ginzburg-Ziv constants for the factors, and so that way we can reduce to the case of a prime. So maybe to write something explicit, one can write this. I think that's it. I mean, even sharper bounds are possible, but this is sufficient for our purposes. So f of z m to the n, if you repeatedly apply this lemma, you can see is at most m times the sum of the s of z pi to the n, where the pi's are the prime factors of m. And so that means if you can bound those, then you can bound this. And reversely, each of those is a lower bound for this. And so that means up to, so if m is constant, this is a constant factor, and the number of summons here is constant. So that means if m is fixed, then up to constant factors, understanding this is the same as understanding this in the prime case. And so that means we can reduce to the case that m is a prime. Okay, so so that means we are now interested for a fixed prime p. We want to understand the growth behavior of s of z p to the n for this fixed prime p and large n. And so then in the second half of the last lecture, which I'm not sure how many people were able to watch it, we also argued that this question is essentially equivalent to the question here. Essentially equivalent in the sense that this Erdös-Ginzburg-Ziv constant s of z p to the n differs by a factor of at most p from the answer to this question. And so the question is, what is the maximum possible size of a subset of fp to the n which does not contain p distinct elements summing to 0? And so I don't want to go through the whole argument again, but just for those of you who weren't here last week and haven't had the chance to watch the video, so the gist of this reduction from here to here is just that you can, so in this problem, all that matters is the remainders of the coordinates of the points modulo m, or here m is p, so modulo p. So that means you can naturally translate this whole problem in zp to the n, so in fp to the n. And so then some points will sort of appear multiple times, right? Because there may be some points which sort of have the same remainders modulo p in their coordinates. So that means you have to account for multiplicities. But everything can occur with multiplicity at most p, because otherwise you find p points whose centroid is a lattice point, and so that's where this factor p comes from. And so that's sort of the heuristic explanation. If you're going to want to go through the details carefully, you can see them on the video. But roughly speaking, it's a simple reduction by just looking at this modulo p to reduce this to this, and then this factor of p that you might lose accounts for the multiplicities of the points. So that means in order to understand this question, all we have to understand is this question. So the question is again, p is fixed, n is large, and we ask ourselves, what is the maximum possible size of a subset of fp to the n without p distinct elements summing to 0? Okay, so then for the rest of today, we focus on this question. And so as this reduction shows, this then gives us sort of, I guess, well, some answer for this question, or some bound at least. Okay, so let's write subsets of fp to the n without p distinct Okay. So we're interested now in the size of the maximum possible size of subsets of fp to the n without p distinct elements summing to 0. So in other words, we're interested in this question. And so for p equals 3, this question is actually equivalent to the question about asking about the maximum possible size of a subset of f3 to the n without a 3-term arithmetic progression. So for p equals 3, Ellenberg and Reisweit proved an upper bound of 2.756 to the n for this problem. And so just to put that in context, so we discussed in the first and second lecture this result of Ellenberg and Reisweit, and this Ellenberg and Reisweit result is about subsets of fp to the n without a 3-term progression. But in the case p equals 3, this question is the same as asking for a set without a 3-term arithmetic progression. Because in characteristic 3, it's the same thing to ask about x plus y plus z equals 0, or to ask about x minus 2y plus z equals 0. So in p equals 3, we're in the very special case that this question is the same as asking about the maximum size of a 3-term progression free set. So this question is equivalent to asking about the maximum possible size of a subset of 3 to the n without a 3-term arithmetic progression. So more generally, Ellenberg and Reiswald proved, as we discussed, this bound for subsets of fp to the n without a 3-term progression for any prime p at least 3. But for primes larger than 3, this question is no longer equivalent to that sort of question about 3-term progression-free subsets. Okay, and so the method that Ellenberg and Reiswald used was later rephrased by Tau. So I'll say using what later became the slice-ring polynomial method. Yeah, so we discussed the history in more detail in the first and second lecture, but basically Ellenberg and Reiswald proved this bound for 3-term progression-free subsets, and then Tau reformulated and generalized their proof to what is now called the slice-ring polynomial method, which we saw in detail in the second lecture. Okay, so now it's very natural to ask whether sort of that proof approach in the slice-ring polynomial method can also be applied to this question for p larger than 3. I mean, clearly it gives very nice results for p equals 3. Maybe we haven't seen the number 2.756 come up before, but we sort of wrote this formula in this result of Ellenberg and Reiswald. And if you plug in p equals 3, you get this number. And so it's very nice because it's exponentially better than 3 to the n. And and more generally, this Ellenberg-Reiswald result for 3-term progression-free subsets of fp to the n is a very strong bound. So you might ask whether this powerful method also applies to this question for p larger than 3, so for p at least 5. And unfortunately, this approach breaks down for p at least 5. So, but for p at least 5, the slice-ring polynomial method approach breaks down for the question above. And we actually already saw this in the second lecture when we discussed the details of the slice-ring polynomial method. We actually had precisely this question at the board, just phrased slightly differently. We had this question phrased as what is the maximum possible size of a subset of fp to the n which does not contain a solution to x1 plus and so on plus xp equals 0 for x1 to xp in the set being distinct. But that's equivalent to this, so this is just slightly shorter to write it. And the reason we wrote it the other way when we in the second lecture was because we wanted to contrast how this distinctness condition really made the approach fail. So for the same question with not all equal we discussed, there was a very good upper bound, namely 4 to the n, obtained by the slice-ring polynomial method. But for this question with the distinctness, the approach breaks down because the relevant tensor is not diagonal anymore. And so that's due to this distinctness condition. Okay, and so that we discussed sort of in the second lecture, how this distinctness condition, I mean, the fact that that makes the tensor not diagonal, so we can't apply Tau's lemma to get a lower bound for the slice ring, and so this approach breaks down. So when sort of this exciting work came out and the slice-ring polynomial method came out, of course people still try to think about how, whether there's maybe ways to circumvent this problem, whether there's maybe ways to still apply the slice-ring polynomial method to this problem. And so in the second part of last lecture, I already started talking about this, but again, because the video was only uploaded on Friday, not sure whether everyone saw it, so let me at least state the important sort of things again. Yeah. So, okay, so the first development in this direction was that Naslund managed to adapt the slice rank polynomial method to again prove a bound for this question which is exponentially better than the ground set size p to the n. So clearly the answer to this question is at most p to the n, right? That's the size of the ground set. And so Naslund introduced a modification of the slice rank polynomial method, which he called partition rank. So partition rank method. So he introduced a modification of slice rank, which he called partition rank. And so using his modification, he was then able to show that the answer to this question is exponentially smaller than p to the n. So as a preprint, this appeared in 2017. It was just only published in the journal in 2020. And so his result says that P at least 3 be a prime. And then if X is a subset of Fp to the n, which does not contain P distinct elements summing to 0, then he proved that the size of X is at most 2 to the p minus 2. So that's some prefactor depending on p. And then the main term is Cp times p to the n, where here Cp is given by this complicated minimization formula, but it's the same Cp as appearing in this Ellenberg-Kreiswald result. So this is the constant in the Ellenberg-Kreiswald bound for 3-term progression-free subsets of Fp to the n. And so, so you maybe remember that Ellenberg and Kreiswald proved, and we mentioned that over there, that a subset of Fp to the n without a 3-term arithmetic progression has size at most Cp times p to the n. So that's this term here, and essentially the same bound up to this prefactor, which only depends on p and is therefore not so important. Naslund proved sort of the same bound for that question here. And so that means in particular he showed that a subset without p distinct elements summing to 0 must be exponentially smaller than p to the n in size. And so maybe importantly, let me mention again that this Cp satisfies (0.84) is at most Cp is at most 0.92. So basically, this bound here is roughly 0.85 p to the n. So that means it's exponentially better than p to the n, and the base here is roughly 0.85 p. Okay, so as already mentioned, Naslund proved this result by introducing a variant of slice rank, which he called partition rank. And so the idea behind this variant was that in the definition of slice rank, a rank 1 tensor was a tensor which could be written as a product, where one factor depends just on one variable, and the other factor depends on all the remaining variables. And so in Naslund's partition rank, what he did was he said, let's allow more factorizations, namely let's look at arbitrary partitions of the variables into 2 non-empty sets, and let's take rank 1 tensor to be something that can be factored as a product of one factor depending on some of the variables and the other factor depending on the remaining variables. So we now allow any partition of the variables into two non-empty subsets, not just partitions where one set has size 1 and the other thing is the rest of the variables. So that means he allowed more such partitions, and so that's then led to his notion of partition rank. And so with this alternative notion of partition rank, I mean, this tensor is still not diagonal for this problem, but he was then able to modify it by adding and subtracting terms in such a way that he could turn it into a diagonal shape, and then he got this bound. Okay, so this proof was sort of not, I mean, this partition rank is very nice and very elegant. The proof was not so easy, though. It was then noticed afterwards by Jacob Fox and myself that there is a much easier proof for essentially the same result, even with a better prefactor here, which was just a very short deduction from this Ellenberg-Kreisweit bound for three-term progressions. So let me maybe just write this in short here. So that was a result of Jacob Fox and myself. Also, so the preprint was also in 2017, and then it was published in 2018. But our preprint was after Naslan's preprint, so the numbers here are confusing. So I say same as above with bound x is size of x is at most 2p times cp p to the n minus 1, which is then at most 3 times cp p to the n. So basically, we improved the prefactor to 3. That's not very important because it's just a constant factor depending on p. The main term stayed the same. And so the point of this was not this improvement in the factor. The point was that we had a much easier proof of this, where we used this Ellenberg-Kreisweit result for three-term progression free subsets of fp to the n as a black box, and then deduced this with a probabilistic subspace sampling argument. And I explained that argument also in the second part of the last lecture. So if you're interested in seeing how this can be deduced in a sort of in a very short proof from this result, then you can watch the second part of the video from last week. Okay, so so these theorems here, the bound here is exponentially better than p to the n, but the base here is roughly something like 0.85p or 0.9p, so the base here is still linear in p. And so for the problem of three-term progression-free subsets, we know that sort of the base linear in p is sort of the right answer, but here we don't. And so the question is, well, is that actually correct, or can that be improved? And in fact, it can be improved. And so the next result improving this was by myself, published in 2021. And it says the following. So again, let p at least 3 be a prime. And then if x is a subset of fp to the n, which does not contain p distinct elements summing to 0, then the size of x is at most cp times 2 square root p to the n for some constant cp only depending on p. Okay, so this next result says that we get in the same sort of setting, we get a bound which up to some prefactor, just depending on p, is on the form 2 square root p to the n. So that means here the base under the exponent n is now only of order square root p, whereas here it was something like 0.85p. So here was linear in p, and now it's only square root p. So that's a significant improvement. Yeah, and what's interesting is that the proof of this also gave a more general multicolored version of this theorem. And so in this multicolored version, the bound is close to tight. So more specifically, for this more general multicolored version, there is a lower bound of square root p to the n for even n. Okay, so this multicolored version is a bit technical to state. So I won't give the complete statement, but it's something in the spirit of, if you remember, the k-colored sum free theorem, which was a generalization. So we saw that in the second lecture, and that was a generalization of this Ellenberg-Kreiswald result for three-term progression-free subsets. And so in a similar vein, there's a multicolored version of this theorem. And so this, again, this multicolored version is more general than this theorem, because sort of you can get this back from the multicolored version. But so interestingly, and the multicolored version follows from the, essentially the same proof. But interestingly, in this multicolored version, this square root p behavior is also the right answer. So there's a simple construction showing a lower bound of square root p to the n for this multicolored version. Oh yeah, and I should maybe say something about the proof. So, so this theorem was proved by combining the slice rank polynomial method, or rather one of its consequences, namely the k-colored sum free theorem, with combinatorial arguments. So putting together combinatorial ideas and sort of this consequence of the slice rank polynomial method, which is called the k-colored sum free theorem, and which we saw in the second lecture, this technical looking statement. So combining that with combinatorial ideas, that was sort of the proof of this result, and the same proof then gave this multicolored version. And so the reason why I'm emphasizing this is because that's at this point sort of a similar situation as for the problem of three-term progression-free subsets of fp to the n. Because there we have this Ellenberg-Kreiswald bound, and then the Ellenberg-Kreiswald bound has this multicolored generalization in the form of the tricolored, so the k-colored sum free theorem for k equals 3. And so for this k-colored sum free theorem, it's known that the base of the exponent is tight. So it's known that the bound is essentially tight, particularly the base, this Cp times P. This is tight for the three-colored sum free theorem, so for this multicolored version of the Ellenberg-Kreiswald bound. But it's not known whether the Ellenberg-Kreiswald bound for this sort of original setting is tight. So for this original setting of just a single subset of fp to the n, it's not clear whether it's tight. But for the multicolored version, it is tight. And it's the same here, or at least at this point, that this theorem proves a bound where one doesn't know whether it's tight for this original setting of a single subset of fp to the n, but it is tight in the multicolored version. And so this tightness in the multicolored version is actually a significant barrier in the sense that whatever proof approaches you might try with the slice rank polynomial method typically will naturally generalize to the multicolored version. So both here, the generalization to the multicolored version is sort of immediate, so it's just the same proof. And also for the Ellenberg-Kreiswald result for three-term progression-free subsets, it's sort of more or less immediate that the same proof gives this tricolored sum free theorem. And so these slice rank polynomial method arguments typically carry over directly to the multicolored setting. But if you know that the bound is tight in the multicolored setting, then that method, at least by itself, won't be able to improve the bounds at all. Because in order to improve the bounds in the setting where you don't know it's tight, you need some sort of argument which doesn't transfer to the multicolored. And so coming up with a sort of way to set up the slice length polynomial method that it doesn't transfer to the multicolored setting, that is actually in some sense a significant barrier. Like it maybe, I mean, it maybe sounds simple, like sort of, if it transfers, great, that gives you additional power, but the point is if you know it's tight with this additional power, then you can't use it to improve the bounds. Yeah, and so in that sense, at this point here, the situation was very similar to how it still is for the problem of three-term regression-free subsets of fp to the n. Yeah, but then relatively recently, Dmitry Zakharov and myself were able to improve this bound, in particular beating this multicolored barrier. So for this problem, we were able to get beyond the multicolored barrier, and I'll sort of explain sort of the proof strategy sort of in the rest of today's lecture. And I still wonder whether some elements of this proof may maybe also be useful to push beyond the multicolored barrier for the three-term progression-free subsets, but I'm not sure. Yeah. Okay. So so the next result is a recent result of Dmitry Zakharov and myself, where we sort of improved this beyond this barrier here. So the result states that for every fixed epsilon, for all primes, and all n, the following holds. So if x is a subset of fp to the n, again, which does not contain p distinct elements summing to 0, then the size of x is at most d epsilon p times c epsilon p to the epsilon to the n, where c epsilon is a constant only depending on epsilon, and d epsilon p is a constant depending only on epsilon and p. Okay, so the statement is rather abstract with all the variables here, but to think about this more concretely, so here you have this prefactor, but the main point of the main sort of term of the bound is 2 square root p to the n. So here you have a p to the 1/2. So the point of this theorem is you can improve this p to the 1/2 to any p to the epsilon for any epsilon you want. So basically, if you want a bound where the base is on the order of p to the 0.01, then there is an appropriate constant here, so that you get a bound like there. So where instead of the 2, you have another constant here, where this sort of main term becomes this constant times p to the 0.01 to the n, and then some prefactor. which may depend on p, and also your choice of this exponent 0.01. But if you think that p to the 0.01 is too big, you can also do the same with p to the 0.00001. You just get a different constant here and a different constant there. So basically, the point is, here is you can make the base to be any sort of small power of p with an exponent as small as you want. You just need to pay, sort of depending on whatever exponent you choose here, by making this constant and this constant larger. So that's what the theorem says in maybe more digestible words with not as many variables. Okay, so that's the statement of the theorem, and it's still the best known upper bound, as far as I know, for this problem. For fixed p and large n, and so particular it leads to the best known upper bound for the Erdös-Ginzburg-Ziv problem for fixed m and large n. And so this upper bound for the Erdös-Ginzburg-Ziv problem is now an immediate corollary of this via the reduction that we sort of saw before. So as an immediate corollary, we get that for fixed epsilon for all m and n, we have that s of the m to the n is at most d epsilon m times c epsilon m to the epsilon to the n, where c epsilon is a constant only depending on epsilon. And d epsilon m is a constant only depending on epsilon and m. Okay, and so that follows from this just via the reduction we saw before. And in fact, here you could even, instead of m, write the largest prime factor of m. But then you need one more variable and the statement looks more ugly. But if you wanted, you also get this bound that this s of the m to the n is at most d epsilon m times c epsilon p to the epsilon to the n, where p is sort of the largest prime factor of m. Okay, but yeah, so this sort of follows immediately from that by the reduction we saw earlier. And so for now, we just focus on this. Any questions? Yeah?
So this bound makes sense for fixed n and m growing?
For fixed m and large n. So as written, it only is interesting for fixed m and n large, because if they are both growing, like, so this, I guess you have a trivial bound of something like m to the n plus 1. And so if n is sort of if n is not growing like this, since we didn't write down what the epsilon m is, this may sort of become larger than m to the n plus n, m to the n plus 1, this trivial bound, if n isn't large with respect to m. Does that make sense? Yeah. So this bound is really only interesting if m is fixed and n is large. But when n is fixed and m is large, then I guess we know that's linear in m. And so now, of course, there's still the questions, what happens when both are large? For example, when m equals n, I think this doesn't tell you anything. And the other thing also doesn't tell you anything. So then I think in the range where, say, m and n are sort of equal magnitude, we still know nothing besides the trivial bounds. Yeah?
In your first talk, you speak about an argument to say that the constant factor, so here d, you could reduce it to 1, not in this case, but in another case, because of if you take
you mean the product argument in the proof of this n-Kreisweit bound? Yeah, so unfortunately that doesn't work here.
That doesn't work.
Yeah, so that's a great question. Unfortunately here that doesn't work. So this product trick sort of doesn't behave well with this distinctness condition somehow. So that's the problem. Yeah. But I mean, in the range where m is fixed and n is large, also this factor is not so important. But yeah, I mean, coming back to your question, if m isn't fixed, then of course this factor does become important. And so then it would be great if we had such a product trick in this setting, but it doesn't work, unfortunately. Okay, so so as you can see, this sort of bound significantly improves upon the previous bound, because now we don't just have square root p here, but any smaller power that we want. But unfortunately, there's still a significant gap towards the lower bound. So the lower bound for this, which we also saw, I think, in the last lecture, had an absolute constant here in the base. So you can get an absolute constant of 2 in the lower bound very easily. So you can get a lower bound of roughly m times 2 to the n very easily. And the best known lower bound, p times 2 to the n in this setting. And the best known lower bound in this setting is something like p times 2 to the 2 to the 2.1398 to the n, so this 2.1398 was the 6th root of 96. Anyway, so it's a constant a bit bigger than 2. But still in the lower bound, this base is still an absolute constant, and so it's a very interesting open problem to figure out what is sort of the right behavior. Should it be an absolute constant, or should it be something slowly growing with p? Maybe slower than this, but should it be some growing with p or not? So that's, I think, a very fascinating open problem. So let me write it here. So can the bound in the theorem above be improved to x is at most cp times c to the n for an absolute constant c? And a constant Cp depending only on p. So basically allowing the prefactor still to depend on p, but can you put an absolute constant here? And as I said, the best known lower bound is of this shape, but we don't know whether that shape is the right answer or whether something growing with p, like there, is the right answer. And I think that's a very fascinating open problem, and I really have no clue which way the answer should go. Maybe as one piece of evidence, one could take that Zakharov, in this work which was already mentioned earlier from a few years ago, he proved that x is at most size p times 4 to the n when p is sufficiently large with respect to n. So that's sort of the opposite parameter regime as the one we were discussing here. So if n is fixed and p is large, then such a bound of this shape was proved by Zakharov, but his arguments do not apply sort of if p isn't very large with respect to n, and in particular they don't apply in this setting. But one could take this as evidence that maybe it should always be an absolute constant. Okay. So, any more questions? Okay. If not, then in the remaining time, I want to give a bit of an overview of the proof of this result. But maybe this is a good point to take our 5-minute break a little bit early, because otherwise we interrupt the sort of proof overview. And then sort of for the remaining, well, about 70 minutes or so, I give a proof overview of the proof of this. And so maybe just as as one sort of little information already, so the proof combines sort of the slice rank polynomial method, or rather one of its consequences, with probabilistic arguments, in some sense similar to this, well, somewhat similar to this argument here for this simple proof, but also with other ingredients from additive combinatorics, namely a higher uniformity version of the Balog-Simarelli-Gauss theorem, and I'll explain that after the break. So let's take a 5-minute break. So let's start again. So as I mentioned, the rest of the time today will be a proof overview for this theorem here. And as already mentioned, one of the proof ingredients is a higher uniformity version of the Balog-Semeredi-Gauss theorem. And so let's maybe first start by, because maybe not everyone knows it, talking about the regular Balog-Semeredi-Gauss theorem, so not the higher uniformity version. And so I wrote an informal version of the statement here, so which sort of doesn't make precise what large and so on means, but that's not so important right now. So the Balog-Semeredi-Gauss theorem states that if A is a subset of Fp to the n, which contains many solutions to the equation x1 plus x2 equals x1 prime plus x2 prime. So if the set has many ways to satisfy this equation with x1, x2, x1 prime, and x2 prime being in the set A, then the conclusion of the theorem is that there's a relatively large subset A prime of A with a property that the so-called doubling of A prime is small. So in other words, the sum A prime plus A prime is not much larger than the size of A prime itself. So here, what does that mean? A prime plus A prime. So A prime plus A prime, also written as 2A prime, is just the set of all possible sums of two not necessarily distinct elements of A prime. So this A prime plus A prime is the set formed by all x1 plus x2, where x1 and x2 are in A prime. And so more generally, we can also say L times A prime as the sum of L things in A prime. So x1 plus and so on plus xl, where x1 to xl are elements in A prime, and again, they don't need to be distinct. So that's the definition of this. Okay, and so what the Balog-Semeredi-Gauss theorem says is if the set has many solutions to this equation, then there's a large part of the set, A prime, so that A prime plus A prime in size is not so much bigger than A prime itself. And so the philosophy behind the theorem is something like if you have a set A prime where this is not much larger than A prime itself, then you will have many solutions to this. And so in some sense, that's sort of the converse, that if you have many solutions, you have to have such a structure, at least for a large subset A prime of A. Okay, so if you're curious about the actual details, what does many and large mean, just to be precise, so let me just say this in words because it's not important for us right here. So the precise statement is if the number of equations to this is clearly at most the size of A to the 3, and if the number of equations is, so that's always an upper bound, and so if it's at least the size of A to the 3 divided by some k, so that means it's sort of on the order of A to the 3, then there is a large subset of this, so that means size of A divided by some power of this k, so that this is by some, at most, some power of k times larger than this, so k to some absolute constant c. And so with that quality of bounds, that was proved by Gauss, but there was an earlier version by Balog and Semeredi with worse parameter dependence, so that's why it's now called the Balog-Semeredi-Gauss theorem. Okay, but so that's not so important for us right here. So maybe the more important question for us here is, how is that at all related to this? So basically what we want to show here is if we start with a subset of this size, then we want to show it has p distinct elements summing to 0. And if you have a subset of that size, you don't necessarily have to have any solutions to this. Right, so you can have a subset of size roughly p to the epsilon n of fp to the n, and you can have no solutions to this. So this theorem is not applicable in our setting. Maybe let me explain why. So we need to show that any subset A of fp to the n of size A larger than d epsilon p times c epsilon p to the epsilon to the n, any such set we need to show contains p distinct elements summing to 0. Right, that was our goal. That was our goal, to prove that statement up there. So we need to prove that any subset of fp to the n of that size must have p distinct elements summing to 0. But the problem is that if we start a set of subsize that size, it doesn't need to have any solutions to this. So any non-trivial solutions to this. So we can't apply this theorem. So, but a set of this size does not need to have any solutions to x1 plus x2 equals to x1 prime plus x2 prime. Okay, so that's why we can't apply this theorem as it is in our setting. And so that's why we need a higher uniformity version of this theorem. So here is this higher uniformity version. So that was proved by Borenstein and Krut in 2011. In fact, there's multiple different higher uniformity versions of this theorem, but this version, due to Borenstein and Krut, was the most suitable for our purposes. So what does that state? So it states that if A is a subset of fp to the n, okay, so we start with a subset A of fp to the n. In fact, it holds more generally in abelian groups, but I specialize it to fp to the n because that's the setting we care about here. And S is a subset of A to the k, which is pretty large. So it's has most, or it's a pretty large subset of all k tuples in A to the k. And so now the next assumption is, suppose that the sums x1 plus and so on plus xk for the k tuples in S. So everything in S is a k tuple of elements in A. So everything in S is of the form x1 to xk. And so for all those k tuples in S, we look at their sums. And we assume that this takes at most A to the c different values in fp to the n, where c is some constant strictly larger than 1. I mean, constant is the wrong word. C is some variable you can choose, and it's supposed to be strictly larger than 1. So then the assumption is that you have a large subset of all k tuples in A, and for everything in the subset, the sums are concentrated on just a few different values. So S is a large collection of all k tuples, but for the things in S, there's only very few different values of the sums. So that's the assumption. And then the conclusion is, maybe before I say the conclusion, let me put that in relationship to this. So if there's a large subset of this where the sums take only few values, then that in particular tells you that there's many different k tuples in S where the sums are the same, right? And so in particular, it tells you that there's many solutions to the equation x1 plus and so on plus xk equals x1 prime plus and so on plus xk prime. And so in that sense, this is a higher uniformity version of this theorem. Okay, and so now the conclusion is that then there is a subset A prime of size A prime at least A to the 1 minus epsilon with L prime A prime being at most A prime to the C times 1 plus epsilon L prime for all L prime. So the conclusion is that there is a large subset of A, so as large subset A prime of A. Again, the size is at least A to the 1 minus epsilon. With a property, so here the conclusion was just about the doubling. Here the conclusion is in fact about all of these sort of multiples. So all for any L prime, the conclusion is that L prime A prime is at most the size of A prime to some power, and that power is this C times 1 plus epsilon L prime. And so I guess this isn't a completely accurate statement in the sense that I didn't make precise what large subset means. But so let me just say it in words. It's not super important for this proof overview, since it's just an overview. But what this large subset means that the size of S should be at least the size of A to the k minus delta, where delta is something depending on this C and this epsilon. So the C you can choose, and it's bigger than 1, and epsilon is between 0 and a half. And after you've chosen C and epsilon, there exists a delta, so that this holds for any S at least size of A to the k minus delta. Okay, so that's the statement. And there's also an assumption that K is sufficiently large with respect to epsilon and C, and that A is sufficiently large with respect to K and C. Okay, but so those sort of fine details don't matter on the level of this proof overview. Okay, so that's the theorem. So now the question is this higher uniformity version of the Barlow-Zimmer-Gauss theorem. So now the question is, why is that useful for us? So in our setting, we start with a set whose size is the set X. So the set X here, we start with a size roughly p to the epsilon times n. And so we want to show that it has p distinct elements summing to 0. So if the size is p to the epsilon times n, then in fact having many solutions, having at most a to the c different values here, or x to the c different values here, that's sort of trivially true if you take c to be 1 over epsilon. Right? Because if you here, I mean 1 over this epsilon, if you here have p to the epsilon n, then the total number of different sums here is at most p to the n. So if the size of A is already p to the epsilon n, then well, clearly we get such a bound if c is sort of 1 over that epsilon. So that means this assumption is now much easier to satisfy. Or if you want to think of it in this terms, in terms of the containing many solutions, if you have a set of size p to the epsilon n, then you will contain many solutions to x1 plus and so on plus xk equals x1 prime plus and so on plus xk prime if k is larger than something like 1 over epsilon. So we are in better shape with respect to the assumption. Like given our subset size, it's realistic to satisfy this assumption for suitable parameter choices. But the next problem is the conclusion. Like, what does this conclusion have to do with the conclusion we want? Right? The conclusion here is that there's a subset which is large with the property that its multiples are sort of reasonably small. So what does having reasonably small multiples have to do with this conclusion? Well, a priori, not much at all. But in order to draw a connection between that type of conclusion, to be able to sort of use that type of conclusion, we work with an inductive framework. So we prove a sort of more technical theorem, which I'll state in a second, which sort of nicely incorporates that type of statement. So it nicely incorporates that type of condition for a set, and so then it sort of inducts on basically the exponent you get here. And so with that inductive framework, we are then able to sort of make use of that conclusion. So basically this inductive technical looking statement is tailored precisely to the purpose of sort of making use of that conclusion. Okay, so let me state this more technical looking theorem. And I guess I can state it here because this theorem we won't use. In fact, let me state it below here. So the technical version of our statement is for every c larger than 1, there is a positive integer L and a constant c of c at least 1, such that for every sufficiently large prime p, large enough in terms of c, there is a constant dCp such that the following holds for all n. And so the statement is, if A is a subset of fp to the n, which satisfies that L times A, so in this sense, so all sums of L elements chosen in A, has size at most A to the C for the C, and A is not too small, so A has size at least dCp times C of C to the n, then A contains p distinct elements summing to 0. Okay, so I mean, as I said, this statement looks rather technical, so the precise sort of order of quantifiers is maybe not that important, but the point is that for every positive c, we start with a set satisfying the assumption that that L times A is at most A to the C, where L is something depending on C, and A is not too small, so A is at least this size. Then the conclusion is that A contains p distinct elements summing to 0. So the upshot is, if L times A is small and A itself is not too small, then A contains p distinct elements summing to 0. And so, so this assumption is, as you can maybe now already guess, made sort of exactly to incorporate the conclusion of this higher uniformity Balloch-Semeridi-Gauer's theorem, so that when we sort of apply that theorem, we get a nicer exponent here, then sort of we get that assumption for a smaller exponent here. So here we basically induct on C, roughly speaking, in the proof of this theorem, we sort of do some sort of induction on C, and there are several cases, and I'll explain that in a moment. But so in one of the cases, we apply this higher uniformity version of the Balloch-Semeridi-Gauer's theorem stated here, and then we get a subset A prime of A satisfying this conclusion, and that the parameters will then be chosen in such a way that this C is actually not the same C as there, so that's a slightly different C, and then that new exponent will be sort of smaller than the previous one, and we can induct. So that's sort of the idea how to incorporate that conclusion. And maybe let me also point out that that step of applying this higher uniformity Balloch-Semeridi-Gauer's theorem in order to pass to a subset A prime of A with this condition, that actually also already overcomes the multicolored barrier. So we also do a similar step in another case, in another setting. So there's sort of basically sort of this step of restricting to a subset we do multiple times, but this sort of restriction to a subset already sort of helps us to overcome this multicolored barrier, because this restricting to a subset like here, that's something you can't do in the multicolored setting. Like, so it's sort of a very simple thing to do, but it is an operation that doesn't transfer to the multicolored setting. And so that helps us to overcome the multicolored barrier. Okay, so this is sort of the technical version of our theorem. So before we start explaining sort of how the proof actually works, let's sort of deduce the sort of main version of the theorem from the technical version. Okay, so let's check that this indeed implies that. So proof of main theorem, and by that I mean the theorem way over there. Proving it assuming this theorem here. Okay, so in order to apply this theorem here, we need to specify our c. In this theorem, we're given an epsilon. So let's just take the c to be 1 over epsilon. And so now, in this theorem, we have a subset x of fp to the n without p distinct elements summing to 0. Okay, and so what we need to show is that the size of this x is bounded by that for suitable choices of these constants. So let's assume for contradiction that it's larger. And so assume for contradiction that the size of x is larger than dcp times cc, and I didn't sort of specify what all these things are, but there will be some suitably chosen constants. Well, okay, so these constants will just sort of come out of these constants. So this d epsilon p will be this dcp, and this c of c will be this c. So we define this c epsilon. So we define this c epsilon to be this c of c. We define that d epsilon p to be this dcp. And so now we want to show that x has at most that size. So let's assume the contrary. So let's assume that the size of x is larger. So that means the size of x is larger than this. And so now we want to get a contradiction. Okay, so we want to get a contradiction by applying that theorem. So in order to apply that theorem, we need to check that condition. So this theorem, so we specified c, so that theorem gives us some L, so that L depends on c, that's sort of given by us by the theorem statement. So let's take that L and look at L times x. So then L times x, well, clearly the size of L times x, we don't know much about L times x, but we know that clearly it has size at most p to the n, right? That's the total ground set size of fp to the n. And so now luckily, p to the n is the same as p to the epsilon to the c, so p to the epsilon n to the c, right? Because c was 1 over epsilon. And p to the epsilon n was already smaller than x, so this is smaller than x to the c. Right, because x is bigger than p to the epsilon n, because these constants are all larger than 1. So maybe we should have said this here, but we can choose them to be larger than 1. Okay, so this means Lx is trivially larger than, smaller than x to the c, just because it's at most p to the n. So that means we satisfied this assumption. We also satisfied this assumption because we just assumed that here. So both of those assumptions are satisfied. So that means by this technical theorem, we get the conclusion that x contains p distinct elements summing to 0. So by technical theorem, x contains p distinct elements summing to 0. But that's a contradiction because we chose a set without p distinct elements summing to 0. And so that contradiction meant that this assumption was wrong, so we get the upper bound on x that we wanted. So this technical theorem really sort of trivially implies that theorem if you sort of look at it right, because you can trivially satisfy that assumption. But the point is, I guess, you trivially satisfy this assumption for rather large C, right? The C was 1 over epsilon. And so I guess basically maybe the magic behind the proof is now to sort of induct on the C. So here sort of, yeah. Okay, so yeah, any questions so far? Okay, so then for the rest of the time, I want to, so now we saw that this implies that, so for the rest of the time, I want to sort of explain sort of, or give an outline of the proof of this statement. Okay, and so let me first explain sort of the main idea of the proof, or basically the main operation we do in the proof. I guess we can erase all of this now because we already saw that this all follows from that. Okay, so here's first sort of the proof strategy in an outline, so explaining sort of the step, the procedure we want to apply during the proof. So in this theorem, we're given a set A satisfying these assumptions, and we want to show that the set A contains p distinct elements summing to 0. So we are given A in fp to the n, as in theorem, and we want to find a solution to the equation x1 plus x2 plus and so on plus xp equals 0 with x1 to xp in A, and our final goal will be to get those distinct. So we want to find a solution to this equation with distinct x1 to xp, right? That's what we want to show. We want to show that there's p distinct elements whose sum is 0. So in other words, we want to find a solution to this equation where x1 to xp are in A and they're distinct. But we don't know how to do that yet. But what we can do is we can find a solution for this where they are not necessarily distinct. So, well, I mean, the first completely trivial way to do this is to take them all be the same thing. So then clearly you can get such a solution. With a slice rank polynomial method, you can also show that you can find a solution where they're not all the same. So we'll see in a moment that we need a little bit more than that. But for now, let's just think we start with some solution here where they're not necessarily distinct. And so now what do we want to do in order to turn this into a solution where they're distinct? So basically, we start with this starting solution. We want to modify it to make all variables distinct. And so to do that, we split x1 to xp into L tuples. And well, since p is a prime, that won't sort of exactly evenly work. There will be some remaining vectors, but this won't be a problem. So let me just write in fewer than L remaining vectors. And so that means we look at this as x1 plus and so on plus xl. That's our first L tuple here. And then plus xl plus 1 plus and so on plus x2l. So that's our next L tuple and so on. And so then there's the next L tuple plus and so on. And so at the end, there will be some leftover things. And so at the end, there will be plus and so on plus xp, where this is fewer than L leftover vectors. Okay, so that's just rewriting this, grouping it in groups of L, and then some leftovers at the end. And so now what we want to do is we want to look at this first L tuple and replace these L vectors by some possibly different L vectors in A. So we want to choose L other vectors in A, or maybe the same if we want, so that the sum gets preserved, so that sort of the equation is still true if you sort of make a replacement here in this first L tuple, but so that we sort of work towards the goal of making everything distinct. And so that means we want our new L things to be distinct from each other and ideally distinct from everything else that appears. And so if we can do this, then we pass to the next L tuple. And so so maybe let's write something down. So we replace this, and then by different L tuple with the same sum. So, and if that works, then we do the same here, and same here, and so on. And so at every step, we want to sort of replace our L vectors by L potentially different vectors, but preserving the sum so that we preserve, that we at every step have a solution to this equation. We want the new L tuple to be internally distinct, so the new L tuples shouldn't have repetitions amongst each other, and they should be distinct from everything else appearing. And if we can do this here, then here, step by step. If we manage to do this until the end, then everything will be distinct, at least assuming if those here were distinct to start with. Like those we don't modify, so we need to make sure that in the beginning there isn't a repetition here. And so basically what we want to do is, because we want to replace this by something where the L variables are distinct, so it's a little bit easier if we always work in the space of L tuples where within that L tuple we are distinct. So basically that's the reason we're already in the starting solution. We can't ensure that everything is distinct, but we want in the first L tuple L distinct vectors. So this should be internally distinct, this should be internally distinct, this should be internally distinct, and so on. And then the remainder should be internally distinct. And so our starting solution should have that shape, that here this part's distinct from, here everything's distinct, internally distinct here, and so on, and also the remainder. And then if we can run this procedure in the end, everything will be distinct. So that's the idea. We start with an L tuple where those are distinct from each other, those are distinct from each other, those are distinct from each other, and so on. And this leftover, sort of here in the leftover things are distinct from each other. And then we replace that L tuple where these L things are already distinct from each other by another L tuple where things are distinct from each other. They have the same sum, but they're also distinct from everything else appearing. And then we do the same here. And then this also becomes distinct from everything else appearing, and so on. And so if we keep doing this, then in the end, everything will be distinct. So in other words, in the beginning, we can have repetitions between different L tuples, but in this replacement procedure, we will, if the procedure works, that we can always replace this with a different L tuple that's distinct from everything else there, then in the end, everything will be distinct. So then in the end, we will be done. Okay, so let's maybe write something down. Okay, so maybe for time reason, let me not write all of that stuff down, but hopefully that verbal explanation was sort of clear. Okay, but so of course this replacement might not work. Like we might get stuck at some steps. So for example, here maybe we want to, so maybe these L things are distinct and we want to replace them by some other L distinct vectors with the same sum, but those are supposed to be distinct from everything else appearing, and maybe that's not possible. So maybe we are stuck. And so that means we might get stuck if the sum of these L vectors has the property that we can't find an L tuple of distinct vectors with that given sum, so that the L things with that sum are sort of avoiding conflicts with what's already there. And so that means the sum might be bad, so that that's not possible. So let's introduce a word for this. So we call W in fp to the n bad. And so that refers to the sum being bad if this replacement doesn't work. So we call W in fp to the n bad if the family of subsets y1 to yl in A with y1 to yl distinct and y1 plus and so on plus yl equals w, right? That's the sort of space of solutions we are looking for, right? if this is some sum W, we want to replace it by some other L tuple in A with the same sum W and where those L things are distinct, right? So that's our search space, basically. So if that family of subsets has a cover of size at most P. So having a cover of size at most P means that among all these possible subsets of size L subsets, so all these possible L tuples that we could put here to replace them, sort of they can be blocked out by P particular vectors, yeah?
So how do you find your starting equation?
I didn't get to that yet. So I was just trying to explain what the strategy is. We get to that point in a moment. So that was sort of roughly the next thing after explaining the strategy. But yeah, you're right. Given these conditions that I said that this should be sort of internally distinct, this should be internally distinct, and so on, it's so far not obvious we can do this. Okay, but so for the replacement, we say that a sum that we might want to replace here is bad if for all possible sort of L tuples that we could put here with that sum, where these L things are distinct, they can be blocked out by up to P vectors. So blocked out means there's that there's P vectors so that if we forbid them, we don't find any such solution anymore. Or I guess in set theory, you can say it has a cover of size at most P. Okay, so if such a sum here is bad, then we might get stuck. If no sum here is bad, then we're happy. So let's say that we call y1 to yl in a to the L with distinct. So we call such an L tuple that might be here with distinct y1 to yl in A bad, just if the sum is bad. So here we defined what it means for a vector to be bad, and now we say an L tuple is bad just if the sum of the L tuple is bad. And so that means if none of those L tuples is bad, so in other words, if none of those sums is bad, then our replacement procedure will work. So then we still have to address the question how to get the starting solution, but at least if we have a starting solution, then the replacement procedure will work if none of the L tuples is bad. So our goal is to sort of find such a starting solution where no L tuple is bad, and then we can run the replacement procedure, and then that will work. And then we find a solution with distinct variables. Okay, so maybe let's write that here. So if we can choose our starting solution x1 plus xp equals 0 such that none of the L tuples are bad. And in addition, every L tuple consists of distinct things and the remainder is distinct, then the replacement proceeds, then the replacement succeeds. Okay, so our goal is to find a starting solution where this is sort of internally distinct, this is internally distinct, and so on. The remainder is internally distinct, and each of these L tuples is not bad. And then we can run this and find a solution where all vectors are distinct, and so we found P distinct vectors summing to 0. Okay, so now the gist of the proof is basically, and we get to that in a moment in a bit more detail, to do a case distinction depending on whether there are many or few bad L tuples. If there are only few bad L tuples, then we do a probabilistic sampling argument to pass to a subset in which there are no bad L tuples left, And then within that subset, we find our starting solution, and so then in particular, none of the L tuples will be bad. So that's the case where there are few bad L tuples. In the other case, when there are many bad L tuples, then that will be the case in which we want to apply this higher uniformity by Lux-Meyer theorem, so this theorem here. And so then we will sort of argue that we can apply that theorem, and then by the conclusion of the theorem, we can sort of pass through sort of the induction on C. So we can apply the induction hypothesis with a smaller value of C here. So that's the rough outline of the proof. So let's see a bit more detail. So of course, for time reasons, we can't go through all of the details of the proof, but let's see at least a little bit more detail. So so the next point is addressing your question about the starting solution. So in order to sort of get the starting solution, we prove the following proposition. And we prove that with the slice rank polynomial method, or rather with one of its consequences, namely the k-colored Sampre theorem. So the proposition says as lambda is between 0 and 1, and let P be a prime which is larger than 1 over lambda, then if A prime is a subset of Fp to the n, and it has size A prime is larger than P squared times C prime lambda to the n for some constant C prime lambda depending only on lambda. So the prime is here because we had a constant C epsilon earlier and I didn't want to double use variables. So if there's this, this is called A prime because we will later apply it to something called A prime. So if you have a subset of Fp to the n whose size is larger than P squared times some constant depending on lambda to the n, then there is a solution to x1 plus and so on plus xp equals 0 with x1 and so on to xp are in A prime such that every vector in Fp to the n appears among x1 to xp at most lambda p times. Okay, so this proposition says if the set is large enough, and note that this large enough is basically only exponential in n. So this is a constant only depending on lambda, not on p. So then we can find the solution to our equation that we want in the set A prime. And this proposition doesn't ensure that these x1 to xp are distinct, otherwise we would already be done and have a much better bound. So it doesn't ensure they're distinct, but it ensures that every vector can't appear too often among them. So at most lambda p times. So for example, if you take lambda at 0.1, then what this says is you find a solution where every vector appears at most p over 10 times. So basically, at most 10% of the things can be equal in the solution. So that's what this proposition says. And so we proved it with sort of combinatorial ideas combined with consequences of the slice rank polynomial method. And so for time reasons, let me not go into the proof of this proposition because I don't think it's the most interesting part of the proof overall. So it's a bit technical, yeah. But yeah, so that's sort of where the slice rank polynomial method is applied. Okay, and so so far this only tells us that things appear not too often in the solution. So in this setting here, we actually want these L tuples to be internally distinct. But so that's now the next lemma, which is just a simple combinatorial statement, which tells us that this is enough to arrange the L tuples in such a way that they become internally distinct. So that's this lemma, again by myself and Zakharov in this paper, where we, and that's really a just simple combinatorial lemma. If we take lambda to be 1 over L, right, then that tells us that everything appears at most p over L times in the solution, which is good, right? Because if we want to sort of have every L tuple distinct, we better make sure everything appears at most p over L times. But so this says that indeed that's sufficient. So for lambda equals 1 over L. If we have a solution with this property, so then each solution 2x1 plus and so on plus xp equals 0 as in the proposition above. Can be split into L tuples in the way we want, so that every L tuple is internally distinct and the remainder is internally distinct. So such that each L tuple consists of distinct vectors and the fewer than L remaining vectors are distinct. And so the combination of those two statements now sort of answers your question, how can we choose the starting solution to get this sort of distinctness? But now we still have to worry about whether these L tuples are bad or not. Okay, so let's now go into a bit more detail on how we sort of deal with the bad L tuples or the not bad L tuples. So, okay, so, okay, I'd like to keep the theorem statement, but I'd also like to keep the definition of bad. So I think I'm forced to erase the stuff I just wrote. But basically, the upshot of this is, so if you, so I'll erase it now, but the upshot is just, if the set is reasonably large, and that really just is rather modestly sized, just sort of exponentially large in n basically, then you can find a solution in that set. So if you find a set A prime, that can be some subset of A, which is sort of at least exponentially large, then you can find the starting solution in A prime so that you can split this with the distinctness condition. So that's the upshot of this here. Okay, so in the remaining 20 minutes, we'll do a sort of outline of the proof of this theorem here. Okay, and so as I already mentioned, the proof is by induction. So now, of course, there isn't really an integer to induct on yet. But if this theorem is true for some value of c, it's actually automatically true for all smaller c's. Like the bigger c it is, the harder the theorem gets. So if we prove it for 10, then it's automatically true for everything less than 10. So that means we can assume that the c is of the form an integer divided by 2. So we may assume c is h over 2 for some integer h at least 3. And so now we induct on h. So basically that means we induct on c in steps of size a half. Okay, so our induction beginning is the case where h is 3, so that means c is 3 halves. So in the induction beginning, c is 3 halves, and we should choose L, so let's just take L to be 2. So let L to be 2, and let A be a subset of fp to the n, which satisfies that A is size at least 20p to the 10, c prime a half to the 2n, and A plus A at most A to the 3 halves. Okay, so that's sort of this condition. So we just define this constant to be 20p to the 10. This constant, we define the c prime a half, which came out of this proposition. And so now this assumption was 2 times A, so in other words, A plus A is at most A to the 3 halves. And so now what we need to do is we need to show that the set A contains p distinct vectors summing to 0. So in order to do this, we run this strategy here with this L being 2. That means we look at pairs of vectors, so pairs of elements of A. So concretely here we know that a pair y1, y2 in A is bad if there are at most p pairs y1 prime, y2 prime in A with the same sum. So with y1 plus y2 equals y1 prime plus y2 prime. So this is sort of just more concretely written the definition over there. So it's bad if there's at most p pairs. If it's not bad, then there's more than p such pairs. So that means there's a lot of flexibility how to replace that pair, and we can't lock it with p single things. So that means the replacement procedure at that step succeeds if the relevant pair at that step is not bad. Okay, so now let's look at the number of bad pairs. So there are at most, I claim, p times A plus A bad pairs. Why is that? Well, for the sum, there's only that many possibilities, right? The sum can only have, the sum lies in A plus A, so there's only that many possibilities for the sum. And so then for each sum, there's at most p pairs with that sum, right? Because that's the definition of bad. So there's at most that many bad pairs, and this is at most, by this assumption, at most p times A to the 3/2. So there's at most that many bad pairs in A. And so now that means we are sort of basically in this case distinction in the induction beginning, we're always in the case where there's few bad pairs. And so in this case where there's few bad pairs, our goal is now to find a subset A prime of A so that within A prime we don't have any of those bad pairs that we had here. So basically we want to avoid any of those pairs and find a set A prime avoiding all of those pairs. So then we can find a subset A prime of A of size A prime being at least p squared times c prime 1/2 to the n, such that there is no bad pair by 1 by 2 with by 1 and by 2 both in A prime. So why can we do this? Well, there's different ways to do it. Sort of in the induction step, we want to do the analogous argument with a probabilistic sampling argument. Here it's actually even easier. So here you can imagine this is a graph, and you want to, where the bad pairs are the edges, and you want to find an independent subset of that graph. You know a bound on the total number of edges of that graph, so you know a bound on the average degree, and then you can use that sort of classical graph theory result that a graph has an independent set of size at least the number of vertices divided by the average degree. And so then you get that there is an independent set of size roughly, so the total number of pairs, so that there's an independent size of set of size roughly a to the 1/2, and so that's then roughly that size. So the details of the calculation maybe don't matter here, but here you can sort of very easily get a subset of that size just from that condition. You can also do it with a greedy procedure if you prefer. Okay, so so that means we found a subset of this size so that there's no bad pair within that subset. And so that means now we can apply this proposition and lemma, which I just erased, to that subset. So by the proposition plus lemma, right, this size is now just big enough to apply the proposition and lemma for L being 2. So for the proposition and lemma, by the proposition and lemma, we can find a starting solution for our process x1 plus and so on plus xp equals 0 with x1 and so on to xp being in A prime. And so again, what I mean by starting solution is that each of those pairs we want to be distinct, but that's sort of guaranteed by the proposition and lemma. The remainder we want to be distinct, well, the remainder has size 1 here, so that's not really a condition, but anyway, that is all condition sort of guaranteed by the lemma, and then just by the choice of a prime, because we apply the proposition and lemma just to a prime, each of those things will be in a prime, and so each of those pairs will be a pair in a prime, and so therefore it's not bad in this sense. So it's not bad in the sense in A. And so that means we can now run the replacement procedure here. Very importantly, at every step where we do the replacement procedure, we can use the all of A. So when we do the replacements, we use the flexibility to go anywhere in A. We don't restrict ourselves to A prime anymore. The restriction to A prime was just for the starting solution in order to ensure that those pairs aren't bad. Okay, so we can then replace the pairs by different pairs in A's. And pairs in A according to our procedure. Okay, so so for time reasons couldn't go into much more into detail, but the point was we run just the procedure I explained here, and that's possible because the proposition and lemma ensured that the original distinctness within the L tuples was satisfied, and the fact that A prime contains no bad pair means that we don't have bad pairs, so we can do the replacement. Okay, so that's the induction beginning. So now we have 12 minutes for the induction step. Okay, and since I again want to keep this and this, I'll erase the induction beginning again. Okay, so for the induction step, let C be again h over 2 as we said, and now h is at least 4. And we assumed that we already proved the theorem for h minus 1 over 2. So, and assume we already proved the theorem for C prime, which is C minus a half, or in other words, h minus 1 over 2. So we assume that for the next smaller C, we already proved it, and so now we want to prove it for this C. So let L be large with respect to C. So how large we won't specify at the moment, but it comes out from sort of applying that condition because here K had to be large. And let A be a subset of Fp to the n. With these assumptions here, so with the assumption that LA is at most A to the C, and A is at least dCp times C of C to the n for some constants which we haven't specified yet, but sort of we'll omit the calculations, but if you do the calculations, you'll see how big you have to choose them. And so what we need to do is we need to show that the set A contains p-distinct vectors summing to 0. So we need to, in other words, we need to show that the set A has such a solution with distinct vectors. And so again, we want to run this sort of replacement procedure, and for that we need to look at bad L tuples, and sort of if we find such a starting solution without bad L tuples, we can run the procedure. And so in order to sort of look at that, we look at the number of bad L tuples. And so here again was the definition of bad. So a sum is, so a vector is bad if the family of subsets of L distinct vectors summing to it has a cover of size at most p, and an L tuple is bad if the sum is bad. Okay, so the first case is if there's not so many bad L tuples. So basically, you make a case distinction depending on whether there are many bad L tuples or not. So if there are at most size of a to the L divided by 2 to the L, p to the 2L, c prime a half to the Ln. So this is not super important right now. So just for completeness, I wanted to write the term. But if there's at most a certain number of bad L tuples in A to the L, then via a probabilistic, probabilistic sampling argument, we want to do the same thing as before. So if there's not so many bad L tuples, and via a probabilistic argument, we can show that there's some set A prime in A which has none of these bad L tuples left. So we can find a subset A prime in A of size A prime at least p squared times c prime a half, 1 over L to the n, such that there are no bad L tuples y1 and so on to yl in A to the L with y1 and so on to yl in A prime. So again, as before, if there's not so many bad L tuples, we find a subset A prime of A, which is still pretty large, namely large enough to satisfy the bound and the proposition, and with the property that inside A prime, none of those bad L tuples in A to the L lie inside A prime. Okay, so this probabilistic sampling argument, I didn't do out the calculation, but it's really, because we only have 6 minutes, I can't do it now, but it's really a very simple calculation to get from there to there. So basically, you just subsample with the correct probability, namely the probability with which you want to subsample every element is 2 times this term, 2p squared times this constant to the n, divided by A, and then if you subsample with that probability, the expected size of the subset you get is twice this, and the expected number of bad L tuples you get is 1, and so you can sort of with iteration argument, just similarly to the probabilistic argument we saw last time, sort of from every bad L tuple in this set you sampled, you delete an element, and then you can sort of really with a very simple calculation get this. So let me not go into more detail, but this is a very simple and standard probabilistic argument to get that subset. Okay, so then if we have that subset by the proposition and lemma, we can find a solution, we can find a starting solution. In A prime, so again with that I mean a solution like here, where internally every L tuple is distinct and also the remainder is internally distinct, and that's exactly what the proposition and lemma guarantee us, given that we had that bound here. And so then, because since we apply that proposition and lemma just to A prime, everything in the starting solution will be in A prime, and so in particular, none of those L tuples will be bad by the choice of A prime. And so that means then we can run the replacement process and succeed. So then there are no bad L tuples, and the replacement process succeeds. Okay, so that means the strategy in this case is like in the induction beginning. So now the question is, of course, what happens if there are many bad L tuples? So that's the other case we still need to do. So assume there are many, and by many I mean more than that number over there, bad L tuples in A to the L. So then each of those bad L tuples has a bad sum by definition, right? So each of them, I claim, can be written in the form y1 and so on to, or can be reordered is maybe better, reordered in the form, so I can permute the vectors in the L tuple to get something of the form y1 and so on to yl minus 1 comma z, where the sum is bad, right? So that's because it's a bad L tuple. And Z is one of the P things in the cover corresponding to W. And Z is one of the P vectors in the cover for some W. Unfortunately, I erased the definition of bad. But a bad L tuple was bad if the sum is bad. So if we have a bad L tuple, then the sum here will be bad. And what does that mean, that the sum is bad? That the sum is bad just means that for all the L tuples in A of distinct vectors summing to that sum, we can sort of block them out by P particular vectors. So in other words, there's a cover of that family of size P. And so that means one of the things needs to be in the cover. So we can put, if we can reorder the L tuple, we can just put the thing in the cover, we can call it Z and put it to the end. So every bad L tuple can be reordered so that that particular vector that is part of the cover for this particular sum W is written at the end, and we call it Z. So just by the definition of bad, which I unfortunately erased, we can reorder it in this way. So now we have at most L times A, which is at most A to the C, choices for W. Right? So there's at most W is in L times A, so that was bounded by A to the C. So we have at most that many choices for W. And given W, there are at most P choices for Z. Right? Because we had a cover of size P, so there's only P things in the cover, so there's only P choices for Z. So that means that gives us a total number of P times A to the C, number of choices for the combination of Z and W, and therefore the sum of the rest, right? Because that sum of y1 to yl minus 1 we can determine just from W and Z. Okay, and so I'm out of time, so I can't go through all the details, but basically the point is because there's only a few possibilities for W and Z, there must be many possibilities for y1 to yl minus 1 concentrated on just few different sums. So let me be a little bit more precise. So with some arguments here, one can conclude that there are many L minus 1 tuples y1 to yl minus 1 in A to the L minus 1 such that their sums y1 plus and so on plus yl minus 1 take at most A to the C minus 3/4 different values. So there's some combinatorial argument going on here, but basically the idea is there's only a few possibilities for W and Z for that combination that then determines the sum. And so now we look at all the possible sums which combine with many different Z's to a bad W. And so if you do that calculation out, you get something on the order of A to the C minus 1, and then there were all these lower order terms floating around, like that denominator here, and you eat them up by changing the C to the minus 1 to C minus 3/4. And so then you can get that. Let me very quickly finish, and then I take your question. Okay, so now we concluded there's many L minus 1 tuples whose sums are focused on just few different values. So that means we are in good shape to apply this theorem for k being L-1. So we now apply this higher order, higher uniformity Balloch-Semmelweis-Gauss theorem by Bornstedt and Kruth here, where we take k to be L-1. So we apply this to these many L-1 tuples with these just few different values for the sum. So the C to which we apply this theorem is the C minus 3/4. And so then we find a subset A prime of A. So then by higher uniformity, the Balloch-Semmelweis-Gauss theorem, we find a subset A prime of A with whose size is not too small. So A prime is at least A to the 1 minus epsilon. So in particular, it's at least A to the 1/2. And also we know that L prime A prime is at most A prime to, well, so here we have C minus 3/4 times this, but altogether that's at most C minus 1/2 if we choose the parameters correctly. And so that means, so that's A prime to the C prime for that particular C prime here, where we already knew that the theorem holds. So we now found a subset A prime of A, which is still reasonably large, and satisfies this assumption that L prime times A prime is at most A prime to the C prime, where we take this L prime to be exactly that L prime from this theorem, which we apply to C prime. So we know that the theorem we wanted to show already holds for C prime, so there's some L prime for which this holds. And so now for that L prime and C prime, we satisfied these assumptions, right? If you calculate this, then you can see that, so that assumption then corresponds to that still being satisfied. This one corresponds to that one being satisfied. So this A prime applies the assumptions of this theorem, satisfies the assumptions of this theorem for C prime. And so that means since we already proved this theorem for C prime, we can now apply it, and we know that A prime contains p distinct elements summing to 0. So that means by induction hypothesis, A prime, and therefore also A, contains p distinct elements summing to 0. Right? Because now in A prime, by the conclusion of the theorem, we find p distinct elements summing to 0. But A prime was a subset of A, so also in A we have p distinct elements summing to 0. So I'm already out of time, so I stop here, but I still take your question.
My question is, how do you reduce the C? Because
you mean with this?
W and all the Z, then I'm of size p times A to the C.
Yes, so the point is there's p times A to the C possibilities for combinations of W, Z, and the sum. So you basically count W, Z, triples of Y, where Y is the sum, Z, and W. And so for such triples, there's P times A to the C possibilities, because there is A to the C possibilities for W, and then given W, there's P possibilities for Z, and then you can calculate Y because W is Z plus Y. So for this, there's P times A to the C possibilities. So now, those different values which you focus on here are the Y's for which there's many different Z's. So let's say we take the Y's for which there are at least A divided by twice that numerator of C's. So that's 2 to the L plus 1. You can see this from here. So 2 to the L plus 1 times P to the 2. I should look at my sheet, but that's faster than running over. So 2 to the L plus 1 times P to the 2L times C prime 1 over L to the 2N. So this numerator from over there, but twice it, therefore plus 1 here. So we look at all Y's with a property that there's at least that many Z's so that we get such a valid tuple. And so for those, we have at most that many. So basically we have A to the C minus 1. So the number of such triples was p times a to the c. So the number of y's for which we get at least on the order of a triples is a to the c minus 1. Right? And the 3/4 was meant to eat up that and that. So the total number of triples is...
Why it falls there, in fact.
What?
A bad tuple, y can be anything. Well, it's some size.
So there's at most that many triples in total, and now we take the set, let's call it capital Y, of all y's with the property that there's at least that many z's, so that yz and w, which is then the sum of y plus z, is one of those.
Yeah,
But then there's at most that many, right? Because y times this has to be smaller than that. So the capital Y is defined as the y's for which there are that many choices for z with this property. So then that gives us a bound for this. But now your next question might be, so why do I know that there's many L-1 tuples with this property, that there's many z's for it? So basically, the point is, we assume that there's many bad L tuples. So basically, there's two different ways how an bad L tuple can be. It can have this sum y, the sum of these y1 to yl-1. It could be in y or it could not be in y. Now for the ones where it's not in y, there's at most a to the l-1 possibilities for y1 to yl-1 with some not in y, and then at most that many possibilities for z. And so this times this is only half the total number of bad things, right? Because we assumed the number of bad things is that many, but that only accounts for half of that number. So there must be, so the half of that number over there, many bad L tuples where this is in y, and then you get that. Yeah. Yeah, so it's all correct, but I didn't explain it because I didn't have time.
Okay.
Yeah.